Welcome to AI Frontiers, where we explore the cutting-edge discoveries transforming artificial intelligence. Today, we're diving into computer vision breakthroughs that are teaching machines to see with unprecedented precision. On August 29, 2025, researchers published 14 groundbreaking papers that are reshaping how machines perceive and understand our visual world. These revolutionary advances span from autonomous driving safety to medical imaging, synthetic data generation, to continual learning, bringing us closer to AI systems that approach human visual understanding. Picture this. You're walking down a busy street, and within seconds, your brain processes thousands of visual details. The color of passing cars, expressions on faces, building textures, subtle movements, indicating someone's next step. Now imagine teaching a machine to do the same thing, but with superhuman precision and perfect consistency. This extraordinary challenge drives today's computer vision research. One day's breakthroughs might hold keys to safer autonomous vehicles, more accurate medical diagnoses, and AI systems that learn continuously without forgetting previous knowledge. Computer vision stands as one of artificial intelligence's most transformative frontiers, representing the scientific quest to give machines the gift of sight. Think of it as building digital eyes that don't just capture images, but truly understand what they're seeing. Unlike cameras that simply record pixels, computer vision systems must interpret meaning from visual data, recognizing objects, understanding spatial relationships, tracking movement through time, and predicting future events. The technology powers facial recognition, autonomous vehicles, medical scan analysis, quality control in manufacturing, real-time sports analysis, crop health monitoring from space, and navigation assistance for visually impaired individuals. What makes computer vision particularly fascinating is its interdisciplinary nature, drawing from mathematics for algorithmic foundations, neuroscience for understanding biological vision, physics for modeling light and optics, and engineering for practical implementation. The field has undergone dramatic transformation over the past decade, evolving from handcrafted feature detection methods to sophisticated deep learning systems that automatically discover complex visual patterns from vast datasets. Imagine computer vision research as a vast ecosystem, much like a thriving rainforest where different species occupy specialized niches while contributing to overall environmental health. In our research ecosystem, 6 major themes represent the dominant species, each playing crucial roles in advancing field capabilities. These themes range from multimodal integration to specialized applications, driving evolution from isolated processing towards human-like understanding. The ecosystem approach reveals how different research areas interact and support each other, creating a robust foundation for real-world deployment. Each theme addresses specific challenges while contributing to the broader goal of creating intelligent visual systems that can operate reliably in complex, unpredictable environments. The first theme, multimodal learning and vision-language integration, represents the ecosystem's apex predators, sophisticated systems combining multiple sensory information types just as humans naturally integrate sight, sound, and language. The VoCap system exemplifies this approach, simultaneously processing videos with text prompts, bounding boxes, or masks to produce both precise object segmentation and detailed natural language descriptions. This integration reflects a fundamental shift from isolated visual processing toward more human-like understanding that combines multiple information sources. These systems can describe what they see while understanding contextual relationships between visual elements and linguistic concepts, creating more intuitive and powerful AI interfaces that bridge the gap between machine perception and human communication. Our second theme, handling uncertainty and ambiguity, addresses one of computer vision's most challenging aspects. Traditional systems often assumed clear, unambiguous answers, but real-world vision is inherently messy and ambiguous. Consider situation recognition research demonstrating how the same image can legitimately be described by multiple different action verbs simultaneously. A person in a kitchen might be cooking, preparing, stirring, and standing all at once. This recognition of inherent ambiguity is leading to more sophisticated systems that embrace multiple valid interpretations rather than forcing artificial certainty. Moving beyond single correct answers, these systems acknowledge that visual understanding often involves nuanced interpretation, where multiple perspectives can be simultaneously valid, reflecting the complexity of human visual cognition. The third theme, synthetic data generation, represents the ecosystem's industrious decomposers, breaking down data scarcity problems and recycling them into abundant training resources. The FLORA system demonstrates this beautifully, using advanced diffusion models to create synthetic images for object detection training. What's remarkable is the efficiency focus, achieving better results with just 500 carefully generated images compared to systems trained on 5,000 images from previous approaches, representing improvements of up to 21.3% in detection accuracy. This quality over quantity approach is revolutionary because it suggests that current trends toward ever larger datasets may be misguided. Instead, focus should be on generating higher quality, more targeted synthetic data, making advanced computer vision development more accessible and environmentally sustainable while dramatically reducing computational requirements. Among numerous advances in these 14 papers, several findings stand out as potentially transformative for the field's future direction. 5 key discoveries could fundamentally change how we approach computer vision challenges. First, DriveQA research reveals a surprising disconnect between general AI capabilities and specialized driving knowledge, challenging assumptions about model transferability. Second, situation recognition. Research fundamentally reframes visual event classification as inherently multi-label due to semantic overlap. Third, synthetic data generation demonstrates that quality dramatically outweighs quantity, with carefully generated datasets achieving superior performance. Fourth, adversarial detection research discovers that adversarial perturbations create immediate detectable entropy signatures in neural network activations. Fifth, atypical video learning research shows that exposure to unusual, diverse data during training consistently improves performance across multiple open-world learning tasks, challenging conventional wisdom about training data similarity. What happens when we combine the most challenging aspects of autonomous driving with the latest advances in large language models? The DriveQA research by Wei and colleagues provides a fascinating and somewhat sobering answer, representing our paper of the day for its profound implications for AI safety and specialized domain applications. The researchers tackled a deceptively simple question: can AI systems being developed for autonomous vehicles actually pass the same driving tests that humans must master to get their licenses? This question opens a window into one of the most critical challenges facing AI deployment in safety-critical applications. The team created DriveQA, an exhaustive benchmark covering both text-based and vision-based driving scenarios that every licensed driver should theoretically handle with ease, grounding their methodology in real driving test requirements, rather than artificial scenarios. The DriveQA methodology systematically tested state-of-the-art language models and multimodal systems across comprehensive driving scenarios, covering traffic regulations, sign recognition, right-of-way rules, and numerical reasoning tasks that drivers encounter daily. The researchers then investigated whether targeted training could address identified weaknesses. What makes this research particularly compelling is its grounding in real-world requirements rather than abstract benchmarks. The systematic approach reveals specific areas where current AI systems fall short of human driving competency, providing a roadmap for improvement. The benchmarks focus on edge cases and regulatory knowledge addresses, pressing concerns in autonomous driving development, ensuring AI systems can handle unexpected scenarios that are rare in training data but critical for safety. The DriveQA results reveal a striking disconnect between general AI capabilities and specialized driving knowledge. While models demonstrate impressive performance on broad benchmarks, they struggle significantly with driving-specific challenges. Numerical reasoning tasks, essential for understanding speed limits and following distances, proved particularly problematic. Complex right-of-way scenarios revealed substantial limitations in current systems. Most concerning, models struggled with traffic sign variations and spatial layout understanding, fundamental capabilities for autonomous driving systems. However, the research provides encouraging evidence that targeted training can address many limitations. Fine-tuning on DriveQA data improved accuracy across multiple categories, with particularly notable improvements in regulatory sign recognition and intersection decision-making. This suggests knowledge gaps aren't insurmountable architectural limitations, but reflect the need for more comprehensive training data, including edge cases and specialized knowledge required for safe driving. Looking toward the horizon, computer vision research is poised to transform from a field focused on individual capabilities to one creating integrated, adaptive, and truly intelligent visual systems. Think of the future like a master artist's studio, when individual tools and techniques combine to create masterpieces exceeding the sum of their parts. The convergence of multimodal learning with continual adaptation promises systems that seamlessly integrate visual, textual, and temporal information, while continuously learning from new experiences. Synthetic data generation is evolving toward intelligent data synthesis, where AI systems will generate precisely the data needed to address specific weaknesses or handle particular edge cases. The integration of uncertainty quantification with robust deployment strategies points towards self-aware visual systems that understand their own limitations and communicate confidence levels to human users. Perhaps most excitingly, the specialization trend suggests a future where computer vision systems become true domain experts. Medical imaging systems matching specialist radiologists, agricultural monitoring systems understanding crop health better than experienced farmers, and autonomous vehicles navigating complex scenarios with superhuman safety records. Today's exploration of computer vision breakthroughs reveals a field in remarkable transition, moving from proof-of-concept demonstrations towards systems that can reliably augment and enhance human capabilities in critical applications. We've discovered how researchers are addressing fundamental challenges in visual understanding, from handling ambiguous situations to creating more efficient and robust systems. The 14 papers examined showcase incredible diversity and sophistication in current computer vision research. From sobering insights about AI limitations in specialized domains like autonomous driving, to encouraging breakthroughs in synthetic data generation and continual learning, these discoveries are laying the foundation for next-generation visual intelligence systems. The implications extend far beyond academic research, paving the way for more accurate medical diagnoses, safer autonomous vehicles, more efficient manufacturing processes, and countless applications that will improve lives and create new possibilities we can barely imagine today. This presentation demonstrates the power of AI-assisted content creation and synthesis. The analysis and narration were generated using Claude's Sonnet 4 model, with text-to-speech synthesis powered by Deepgram technology and image generation through OpenAI systems. While human expert review ensures quality and accuracy of the synthesized content, some oversights may exist in this AI-generated analysis. All original research references are provided for verification and deeper exploration. This approach showcases how AI tools can help researchers and educators process and communicate complex scientific information more efficiently, though human oversight remains essential for ensuring accuracy and contextual understanding of specialized technical content. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from archive preprint server. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates on cutting-edge AI research insights, weekly deep dives into breakthrough papers, expert analysis of emerging technologies, and community discussions on AI's future. Stay ahead of the artificial intelligence revolution with AI Frontiers. See you tomorrow with more cutting-edge AI insights. Disclaimer: this video uses archive preprint server content under its API terms of use. AI Frontiers is not affiliated with or endorsed by Archive Preprint Server.